Hey everyone, my name is Max. I'm a researcher from TogetherAI, and the subject of my talk is going to be drawing connections in decentralized deep learning. The idea of the presentation is actually like to consolidate a lot of different threads and research directions that are happening in decentralized deep learning. Over time, there are some more prominent directions or like less prominent directions. So I'd like to kind of connect all of them, starting with the motivation, and go over some of our research that like I've done during my PhD and beyond that. Also, I wanted to highlight some of the key learnings we've made during that research, hoping that it will be helpful for future collectives who conduct their work in the same area, and also outline a couple of questions for future work that might be relevant for people who are excited about the field in general. So let's start with a disclaimer. First of all, a lot of the papers that I'm going to talk about are probably from the pre-ChatGPT era, so they might be not as like large scale or LLM centric as you'd expect. Regardless, the ideas expressed there are quite valuable, and you will see that they find like very interesting manifestations in more recent work. Secondly, there is a lot of literature in this field in general, so I am definitely missing some of the important works here. Let me know after the talk which most interesting, like which most relevant papers I've missed. I'd be happy to include that in the next iterations. And yeah, lastly, because I've done some research in this field as well, the perspective might be a bit biased. So I'd like to start with this plot, which is from a recent publication by Epoch AI that shows the growth of deep learning compute over time. So like since 2010 until 25. And as you can see, the number of compute that is required in flops to get like frontier models grows by like 4 times per year. And as a result, you can understand that if you're just like an independent researcher or if you're doing work in academia, it might be a bit hard for you to advance the field because simply reproducing the experiments might be a bit difficult. So what should we do about this? One idea that stems from other fields of science is to use volunteer computations. So is there anyone in the room who's familiar with projects like Folding at Home or SETI at Home or Boeing? Yeah. Yeah, well, quite a few of them. So yeah, like for those who don't know, it's basically an approach which allows you to leverage the idle resources of volunteers who would be able to contribute to a specific experiment, like in protein folding, if I remember correctly, or discovery of extraterrestrial civilizations by connecting your home PC and donating the idle GPU resources of it to the goal of running computational experiments. So the idea originally, at least for us, was quite simple. Let's try to apply the same technique for deep learning somehow, because there's a lot of idle compute. Maybe we can leverage it somehow. To make things clear, actually, our idea was not definitely the first in the field. Some of you might be familiar with this project called Little Chess Zero, which was started in 2018, if I remember correctly, and targets a very particular, a very similar goal. So the authors wanted to create a chess engine that would be trained, trained in this volunteer training setup, and it's been pretty active and pretty successful. So as far as I understand, it actually won some chess engine competitions. So the whole initiative was quite successful. However, this approach is relying on the fact that the data generation for things like reinforcement learning is very easily parallelizable. You can generate lots of games, you can play those games with a model. So it's quite straightforward to distribute to all of the volunteer GPUs. However, in our setup with volunteer distributed deep learning, where we want to train large models, there are quite a few very particular challenges that might be specific to the setup. So the first one is the issue of node failures. Usually, when you launch something in a cluster, obviously not always, you can expect that the nodes will remain stable. They will not randomly turn off, turn on, and like the connections would not get dropped. This does not hold for the larger scale runs, but still. The second issue is that the communication speed over the internet is magnitude slower compared to high throughput interconnect that you get in the clusters. So this is also a very important problem which some communication efficient methods aim to address. The third issue is that each home computer is different in some sense. So you can have people joining with different GPUs, with different connection speeds, and the methods that you design have to take that into account, because usually you assume that the overall computation load can be spread equally. So the first approach that we've tried was called learning at home, and the idea was relatively straightforward. So there are particular classes of deep learning architectures that, in our opinion, were more susceptible. Like it would be easier to adjust them to this decentralized heterogeneous setup. The name of those architectures is kind of evident from the title. It's decentralized mixture of experts. So to explain how that works, let me first ask how many people here are familiar with mixture of experts in general. Way more than with volunteer computing, as I expected. So the idea is very simple. You have a particular layer of your model, and let's say that it can be separated in multiple independent subnetworks, which are called experts here. Now, for any particular input, we can have multiple experts which are activated for token, for like a sequence, depends on your MOE implementation. The key idea here is that we can allocate different numbers of experts on different peers in our network based on their GPU memory, based on their performance characteristics, and so on. So now we can locate those peers using decentralized key value storage systems like DHT, and then like we send the activations to them and aggregate the output. One other addition here is that if some of the experts do not respond, you can just ignore their output in case you requested multiple and proceed with other experts on other nodes. So this architecture is kind of fault tolerant by design. The idea here, like for training larger models, is actually not the first idea to train things in decentralized manner overall, because decentralized SGD for data parallel training was an approach that was proposed way earlier, like for data privacy reasons first, and then for communication efficiency, and studied a very particular setting. So formally, the parameter server architecture where a single node communicated with everyone was like a very prominent idea in distributed machine learning. The key insight of decentralized SGD, at least to me, is that you can exchange your updates with neighbors iteratively instead of the complete network. So this is kind of like more fault tolerant and also a bit more communication efficient because you don't have to wait for everyone. So yeah, like this was proposed first for data privacy, and in further papers, we've seen that it can result in training performance gains, as in speedups, and can be extended to arbitrary communication topologies. So decentralized SGD is a very interesting approach in this regard. Next, I also wanted to point out that this idea of running SGD on arbitrary topologies was extended in another way. So we can actually do communication not in a bidirectional way, but in a unidirectional. You can push your updates, your new parameters to some participant, and then maybe you, like the receiver, will get them in time, maybe they will not, but the idea is that over time, assuming that the network is somewhat stable, it will converge and like improve your results compared to a single node. So the family of those methods that communicate updates over graph is called gossip, and there have been a couple of papers by Meta in like 2019 and 2020, which were, in my opinion, like very influential in this field, because they've shown that this can actually work for models like transformers on machine translation setups, for ResNets on classification, and in fact, the slow-mo paper, which was at iClear 2020, shows that this approach can be extended with a momentum after like periodic exact averaging for further boosts. So the ideas were like very, very influential for our next work. Here we try to, here's slow-mo. Here we try to identify what to do in the cases when we still want to do like standard all-reduced like averaging with full data parallelism, but we want to be more fault tolerant. For those who don't know, if like usually a single peer gets disabled or disconnected from the all-reduced protocol, it can very likely result in the failure of the entire communication collective. So our idea at the time was to try and average the parameters in the gradients in smaller non-overlapping groups, so that like in the end it results in getting the exact average. Here's the illustration. So let's assume we have 9 nodes, like 9 different sets of parameters, and we want to compute the average of them. Let's arrange them in this kind of a 2-dimensional grid, and in the first round only do averages in groups of 3, like the horizontal ones. So now we've computed their average, and then we proceed to the second round, where horizontally all parameters are the same, or gradients, and then you can do the same thing across the second dimension. So at the end you still end up with the correct average, but the benefit is that if you fail at any point in time, only a smaller group would fail and not average completely. So that's the broad idea behind MOSFET-HDD, and in our work we've shown that it can result in communication and convergence accelerations. In fact, however, after some time, we've discovered that the idea in general for running all-reduced in groups was not introduced in MOSFET like first of all. So you can see that different approaches to running distributed training efficiently can come from very different fields. So we've found this paper, which was called Weight Awarding Group Averaging, or WAGMA-HDD, which expresses at the core the same idea. Let's try to do partial aggregation of gradients or parameters in those non-overlapping groups, and sometimes do the full global averaging. And in their work, they've demonstrated like some very, very substantial speedups for transformer training and even RL compared to state-of-the-art decentralized methods at the time. So please check out that paper. After that point, we've stumbled upon the next problem when trying to scale it up to more heterogeneous groups of volunteers. Let's imagine that we have people from like with different devices, different GPU speeds, and we need to somehow adjust to that. So how to do it? TLDR, we've tried to design the averaging algorithm, kind of like a modification of all-reduce, that would adapt to the network conditions and try to come up with the most efficient averaging schedule in each case. So the advantage, or kind of like a very neat property, is that in special cases like equal bandwidth or one specific fast peer, the method just recovers regular distributed training methods like all-reduce or parameter server, or like in more special setups, it's a hybrid approach. So next up, if we have participants with different speeds, you can actually just do large batch SDD to a certain point and do gradient accumulation. So let's assume you have multiple participants and they have different speeds because of different GPUs and so on. So let's try to accumulate the updates and then synchronize only when the target batch size is reached. The simple trick here is that if one peer, like peer 4 here, disconnects from the network, it will easily, we will easily compensate for them by just spending a bit more time on all the other devices, on all the other machines. And vice versa. If we have an additional participant who joins the network, we speed up automatically because the updates will be accumulated faster. So this is kind of like very standard gradient accumulation, just applied to a different setup. The combination of all of those approaches allowed us to train a language model, a reasonably small one, in a collaborative setup back in 2021, in collaboration with folks from Hugging Face and the community of around 40 volunteers. So the model was called Bird, and it's a modification of Albert Large for the Bengali language. The participants used a lot of different environments to connect to this experiment. They've joined from their virtual machines, from their home servers, and some people even from Colab or Kaggle instances. So here in the plots, you can see the distribution of GPU types and even like the plot of activity over the duration of our experiment. So surprisingly, or maybe not so surprisingly, we've achieved results that were competitive to state-of-the-art models trained on regular, densely connected clusters for the Bengali language benchmarks. If you'd like to learn more, there is a blog post that we've written together with Hugging Face, so you can learn more details about it. Next up, we've done the slightly larger training experiment for a different domain, applying basically the same sort of techniques, but for a different generative application. So here we're trying to train a text-to-image model similar to the first version of DALL-E with volunteers as part of a new RIPS demonstration in the same 2021. Again, the core techniques were more or less the same, and some of the optimizations we've made was just to make it easier for people to join the experiment and immediately start training. So here we've preprocessed images with VQGAN to obtain discrete code, uploaded them on the Hugging Face Hub, and allowed participants to stream directly from it. So it resulted in around an 18 times speed up in terms of the bandwidth. The run lasted for 2.5 months, and there were 37 volunteers who contributed significantly with our compute. All of the results, the code, and even the plots, if I remember correctly, are available in our report and on the website. So the next question was to try and scale that to setups that would be beyond a single GPU. So we kind of understood at this point how to train on a single device setup, and now we wanted to break down the model and chart it in some way to make sure we can scale to like 10B, 70B, or beyond. And the approach we've suggested here was to leverage regular pipeline parallelism, but make sure that we can rebalance the layers based on their performance and based on the average composition of the network over time. So in essence, we have this composition of different stages, like as in standard pipeline parallelism, but whenever a device leaves the network because someone decided to play a game or something, we can identify the least occupied stage at this point and make a transition between stage 3 and stage 2, as in this example. So yeah, we've tested it in considerably large-scale setups in our paper, and the approach has some disadvantages, as was already discussed today in the workshop, but at the time it was a very interesting result for us. So after we've done all of that work on training in different collaborations with volunteers, one of the first lessons we've made was that trying to do deep learning with volunteer computing is difficult. So it's not only because of the reason that training can be very long, but encouraging volunteers to join for a sustained period of time, like weeks or months potentially, depending on the scale of the model you want to train, requires some motivation for them. So it either has to be a model that doesn't exist anywhere else or is not addressed by the community, or there needs to be something else to incentivize them. Also, as other machine learning collaborative projects have likely identified as well, developing a high-quality model is not just a matter of compute, obviously. Well, obviously in hindsight. There also needs to be the model architecture design work and the data recipe, crucially, that would make it all like worthwhile when combined together. And this can be quite difficult to coordinate if you just have like the volunteers contributing compute, but not that many people thinking about what model you want to train. Yeah, I was also very lucky to participate in a couple of Boeing workshops that were organized by Berkeley. And one of the materials I've read was the blog post by David Anderson, so like the author of this entire field of volunteer computing, at least in my opinion. I highly recommend reading this blog post because it outlines the entire history of this project from a very different field and like from a different perspective. So yeah, it's likely going to be very interesting if you're excited about this field in general. The second lesson we've taken here was that originally our goal was potentially a bit too ambitious. And this is a lesson that might be useful for research in general. So as you might remember from the earlier slides, our approach was to try to train neural networks over the internet. We wanted to train large models with volunteers who can join or leave, and some of them can be malicious. I didn't mention the security work here, but it's also an important consideration. So as you can imagine, solving any particular problem is quite challenging. And of course, we got kind of nerd sniped by particular sub-problems in this area, which reduced the focus. And we've addressed all of them to a certain degree. But on the other hand, there are certain goals for running all of those experiments, or like for this research area in general, that could be more important in the broader context of just training large models in, for example, communication constraint setup. So prioritizing them could likely produce stronger results, and I'm very excited to see more and more works like in parallel and like afterwards trying to tackle this particular field. One specific line of work that I wanted to highlight here is trying to train with local updates to reduce the communication footprint. The idea was outlined in multiple different papers, and the approach is just to make SGD steps without communication on each node. So compared to standard SGD, where you have multiple workers who later on aggregate their gradients with any kind of procedure, you do a different thing. So you try to run multiple local updates, and then at the end of the outer iteration, you apply a step. So this approach allows you to do like great communication savings, because the more local steps you do, the more communication you save, because you don't have to share it with others. This work has benefited from extensive theoretical analysis, basically from the start of like the work in this field of communication efficient training. This was a very interesting idea. It can be extended to setups like heterogeneous compute, data compression, and obviously I think everyone who's here in the audience knows that Loco and all the work that happened in this field show that it can work successfully for LLM training in a very specific setup. So yeah, local training is a very exciting approach in this direction. I also wanted to give a very, very quick sneak peek of some other projects that are brewing up in this space, and are trying to apply those same ideas and to prove them at greater scales than what we have right now. So, for example, there is a question of how scalable can we make all of these family approaches in general, just to make sure it can work for large models. There are some successful results already, like Intellect 1, which has shown that it can work at the 10-bit scale. Please correct me if I'm wrong. But if we wanted to scale it even further, like 70B, it can be quite tough. So the idea is to gather resources from different data centers in the industry and academia, and scale up methods like Loco, understand if they can be applied in broader conditions, and probably like stick to the standard recipes on all other axes. Yeah, for inference, I'm going to be very brief, but we've tried to extend the same approach as Swarm to just running models. And this is what we've done with pedals. So here the idea is to load layers on different GPUs, allow others to run forward and backward passes. And the simplicity of it is what probably enabled a slightly a slightly broader success of pedals compared to the training approaches that we've done. So yeah, here's the outline. It's kind of comparable to Swarm. And the main takeaway from me was that if you wanted to make volunteer-based projects successful, it's very important to make it easy to start contributing to one. So compared to training, here you can just join the existing network and start running inference already, because the model is pre-trained, so you don't have to wait until it gets good. So it's kind of drop-in compared to training. And we've developed, Alex, as the main author of Pedals, has developed a lot of simple tools to make joining and running inference with Pedals easier. And this has also contributed substantially to the interest in this entire field. So yeah, that's the primary takeaway we've got for Pedals. Last but not least, I wanted to pinpoint that the majority of work that we've done in this field was made available and made possible by HiveMind, which is a framework on decentralized training in PyTorch that we're developing since the very first paper. It's fully open source. It's available as a Python package. In fact, we've just published a release last week, so like the latest update. It offers techniques like peer-to-peer communication, asynchronous training, so it's relatively easy to use in basic setups. So yeah, if you're interested about this entire field, feel free to take a look at it and contribute. In particular, there have been some projects like Pedals by Big Science, OpenDLoco by Prime Intellect, or RL Swarm by Jensen, who have leveraged HiveMind in one way or others to make decentralized deep learning easier for them. Yeah, so as a conclusion, decentralized deep learning can be a very interesting alternative to single cluster training. The field could benefit and benefits already from a lot of prior and parallel research in other areas of machine learning. And some of the promising directions are trying to scale training to larger models, designing low communication model architectures like DeepACO or decentralized MOE, and understanding what should we do to train sustainably with volunteers. So yeah, thanks everyone for your attention.
Have you got any exciting resources for looking into lazy nodes or malicious nodes?
There is basically the whole field of Byzantine tolerant federated learning, which tries to tackle this particular idea. We've done a bit of research in this field as well. I just didn't mention the paper because of time constraints, but it's called Secure Distributed Training at Scale. And overall, all of the papers on Byzantine tolerance for distributed training are something that could be potentially leveraged to solve problems like with faulty nodes or with malicious participants who don't share the correct gradients, trying to steer the training in some other direction.
Thanks for the talk. You mentioned we haven't trained 70 billion parameter model with this approach yet. So what was the largest model that you are aware of that was trained through decentralized methods? And secondly, is there any particular characteristics of these models? Because the synchronization happens late. So do these models behave any different from the models that are not trained in this way?
Yeah, thank you for your question. So again, to the best of my knowledge, things happen too quickly these days, but the largest model that was trained in a decentralized way was Intellect 1, which was done in late 2024. It's around 10 billion parameters. Maybe there was something else, so please let me know if I'm wrong. In terms of the model behavior, I haven't observed any specific differences to regular setups, and probably it's because of the fact that a lot of the methods try to make the training dynamics very comparable to regular standard non-centralized training setups. So in terms of model behavior, no. In terms of the training dynamics, we've actually tried to see if it should be different, but it wasn't that much different. So it converges relatively in the same way, stepwise.
So training with local updates and infrequent synchronization is great, but it's not fault intolerant. So in your system of volunteer, I assume faults can be very frequent. So and like if you do local updates, that means that you will lose all the information and other nodes become idle, waiting for the synchronization and so on. So how do you overcome this? Is there a solution?
Yeah, that's a very good question. I don't know the right answer here, obviously, but in principle, if we consider like other ideas in the space, it should be possible to aggregate the like average the results only from the peers which are online at a particular point in time. So yes, like one worker can disconnect, we can lose their results, but maybe in deadlock style training we can compensate for them with other participants, or we can just ignore it and say that yes, we didn't make a very accurate gradient descent steps, but because we make them very frequently and because we have lots of compute, we can compensate for that. Yeah, it's mainly about trade-offs, I would say, here.
NVIDIA recently announced Dynamo, right? That's for inference. But do you see any ideas from that can be actually, again, training, inference have different bottlenecks, but are there any ideas from that you see can shape how you do distributed training?
Yeah, so I will give a very brief answer here because I'm not very familiar with like distributed with the approach of Dynamo in particular, but my answer is yes. So there are like lots of techniques in inference acceleration and like in distributed computation in general that could be applied to make like setups like pedals or setups like Dynamo, vice versa, more robust first and more efficient second. So yes, but we need to figure out the details.
I'm curious about the sober comparison works to the reference training. So I guess people would like to know to adapt this how much you suffer in terms of training speed if you go for asynchronous algorithms in general. How much do you lose in terms of the resulting model quality compared to a reference algorithm? Is there anything out there? So I was looking at the most recent DeLoco scaling laws work, and there I had a feeling that the downstream task evals are somewhat very narrow, so not really reporting a lot of scores, mainly using the loss. So is there a reason for that in the community? Because I mean, downstream evals are easy. It's not.
Yeah, I'm not aware of it in particular. I can only hypothesize here. So maybe like from our perspective, potentially, if we try to train like the same model on the same data and maybe it converges slowly, the behavior on evals in particular would be more or less representative of what you'd get in those results. So maybe we just treat it as an optimization problem instead of like getting a good model problem, and that's kind of like the next step for us to make. Overall, I agree that running downstream evaluation shouldn't be that hard. It's like super parallelizable, so it should be easier. But yeah, I think like the question is how to make it train in the first place, and the question of like how to make it replicate the behavior of a model is secondary, not because we don't think it's important, but because like the first problem is more challenging for this particular setup. So yeah, that's my opinion. Maybe Arthur has some others.
What are projects in your area, right, in deep learning, where you see the community, being incentivized without money to spend their compute, and it actually takes off a little bit like City at Home?
That depends on how you view it, to be honest. So I would say that in general, like I have a very good example, but it's not about compute at all. So we have the like broader open source machine learning community, which does a lot of things being completely unincentivized by anything. So I would say that those contributions are definitely very visible, very impactful, and very important. So like people building models, people like merging models sometimes to get better results, and it's very simple thanks to the simplicity of merging methods. People trying to collect high quality data sets and publishing all of it like for others to build upon it. So I would say that this like brain and like personal power of people contributing in this regard is probably like the most important example I can give. But yeah, maybe I'm just like trying to think and cannot think of anything more visible in the space. There's definitely something else. Yeah, I'm just yeah. This is just the first thing that came to mind.
Again, in the context of not knowing who contributed to run, do you know if there's ways to tag which peer contributed which piece of data to potentially do attribution down the line, whether it is from the outputs or of the model weights, which might address part of the incentive problem down the line when the model is out in the wild?
Yeah, so that's a very good question, and we've proposed a very simple approach in the paper Secure Distributed Training at Scale. I realized I should have included it in the slide, but it would be too long. So the idea is that you can try to record all of the training steps, all of the batches that any particular peer went through, like for any intermediate iteration of training. And you have a subset of trusted participants who are like validators who then try to reproduce the training results, because like all of the checkpoints should be ideally public. So you should be able to reproduce the update that they should have obtained by going as intended through the training. So if they complied, if they were like, if they behaved as expected, then it's kind of like, so you know they are not malicious. So then you can incentivize them. You can do no. So like that's the problem. So like unfortunately, I'm not familiar, but maybe it's possible to simplify it, like do the verification somehow. But the simplest thing we could think of is just to like verify some small percentage of random peers every time, and then hopefully like the bad ones will be detected. Yeah.